Any desires for finding some sort of extraterrestrial life inside our own nearby planet group once experienced a blow with a new paper proposing Saturn's biggest moon is likely fruitless. However, later concerns have arisen about the probability of alien life inside our nearby planet group. A dazzling disclosure by NASA has changed the hypothesis: life has been detected on Titan, Saturn's greatest moon. Titan, a celestial body that represents the universe's extraordinary diversity, now entices with new interest. Despite its seemingly empty appearance, Titan seems to harbor life forms unlike anything we've ever seen. What new discoveries has the scientific community made on Titan? What lies beneath the surface of Titan's cloudy lakes? What mysteries do its frozen landscapes conceal? Does Titan harbor living things like those on our own Earth? Join us as we explore how NASA finally found life on Titan and the astounding new discoveries on Saturn's moon. Titan is Saturn's greatest moon and the second largest in the solar system, surpassing all the solar system's dwarf planets. It is the only moon known to have a thick atmosphere, as well as the only known object in space other than Earth with clear evidence of stable surface liquid bodies. Titan is one of Saturn's 7 gravitationally circular moons and is the second most distant of them all. Titan, often referred to as a planet-like moon, is half again larger in diameter than Earth's moon and 80% more massive. It is the second largest moon in the solar system, after Jupiter's moon Ganymede. Titan is larger than Mercury, though only 40% as massive, due to Mercury's composition of hard iron and rock, while Titan is made primarily of less dense ice. Discovered in 1655 by Dutch astronomer Christian Huygens, Titan was Saturn's first known moon and the sixth known planetary satellite. Titan orbits Saturn at 20 Saturn radii. Saturn subtends an arc of 5.9 degrees from Titan's surface, and if visible through the moon's thick atmosphere, it would appear 0.4 times larger in diameter in the sky than the moon does from Earth, which subtends a 0.48-degree arc. For a long time, this moon, almost twice the size of Earth's moon, was viewed as the most viable candidate for alien life in the planetary system. The Huygens Atmospheric Structure Instrument, HASI, conducted the first in situ observations of Titan's atmosphere. It measured atmospheric temperature, pressure, and density from as high as 1,400 kilometers down to the surface. Long before the ESA's Huygens mission landed on Titan, scientists knew that the moon's thick atmosphere was primarily made of nitrogen, with some methane. However, the structure of the atmosphere, including temperature and pressure at various altitudes, was poorly understood. The HASI equipment directly assessed the density of the upper atmosphere by measuring the probe's deceleration rate as it descended into the atmosphere. The temperature was determined using predictions of how it should vary with density and altitude. HASI directly recorded pressure and temperature in the lower atmosphere, below 160 kilometers, and on Titan's surface, as well as electrical properties including permittivity and ion distribution. HASI's data revealed that the upper atmosphere, the thermosphere, was warmer and denser than expected. Titan's atmosphere was also found to be highly stratified. At altitudes above 500 kilometers, the average temperature was around -100 degrees Celsius, although significant variations of 10 to 20 degrees Celsius were observed due to inversion layers and phenomena like gravity waves and tides. Contrary to theoretical projections, the mesosphere was almost completely absent. Temperatures rose sharply below 510 kilometers, peaking at -87 degrees Celsius at the top of the stratosphere at 250 kilometers altitude. The temperature then gradually fell throughout the stratosphere, reaching a minimum of -123 degrees Celsius at 44 kilometers. This marked the boundary between the stratosphere and the lower atmosphere. The temperature increased again as the probe approached the surface, reaching a frigid -180 degrees Celsius at the landing site. The surface pressure was 1.47 times higher than on Earth. Various other instruments, including the Hubble Space Telescope and Cassini orbiter instruments, were used to measure Titan's atmosphere. These measurements identified evidence of gases that suggest organic compounds. After the Cassini-Huygens mission, it was found that many of Titan's lakes are most likely composed of liquid methane rather than water, which was initially disappointing but kept the mystery of whether life could exist on Titan alive. Titan, Saturn's moon, is a fascinating world that, from a distance, resembles a greenish-brown counterpart to Earth. In fact, Titan and Earth are the only known celestial bodies in the solar system with stable liquid bodies on the surface. The Huygens mission, with twin spacecraft launched from NASA's Florida spaceport in October 1997, was destined for Saturn and Titan. It explored Saturn for nearly 30 years, while the lander's lifespan was expected to be much shorter. Huygens had one purpose from the very start: to fly through Titan's atmosphere and land on its surface. On December 25, 2004, the moment came. Huygens separated from Cassini, and 2 weeks later, the lander descended into Titan's atmosphere, hanging on a parachute. Huygens spent 2 hours and 28 minutes collecting data in the atmosphere before landing on the surface and gathering data for an additional 56 minutes. Since those crucial hours, we on Earth have learned much more about Titan's true nature, but the mission has yet to answer all the puzzles surrounding this intriguing moon. Titan's atmosphere is rich in nitrogen, much like our own on Earth, with large amounts of methane, hydrocarbons, and evidence of organic molecules. Titan has a nitrogen concentration of 98.4%, with no oxygen in its environment. Methane exists in the higher layers of the atmosphere because of its low density. Curiously, different natural particles such as ethane, propane, ethene, and hydrogen cyanide were found. Hydrogen could also detect traces of helium, carbon dioxide, and water. Despite nitrogen's significant impact on Earth's processes that allow organic life to exist, the environments of Titan and Earth contrast considerably since Titan has no oxygen. Since the mission began, planetary researchers have used the Cassini spacecraft radar system and the Visible and Infrared Mapping Spectrometer, VIMS, to analyze the composition of the region. Before Cassini's Huygens probe sailed across Titan's surface, it was a complete mystery, obscured by a thick cloud. As the probe entered the layer of dimness within the atmosphere, it revealed a previously unseen world. According to Jean-Pierre Le Breton, ESA's Huygens project scientist, Lorenz Sodom of the U.S. Geological Survey has been working to decipher what Huygens observed. Finding Huygens' landing location in Cassini photographs proved one of the most challenging issues. When scientists compared synthetic aperture radar images to VIMS data, they saw little correlation, Sodom explained. Lorenz Sodom, known for his contributions to imaging science, served as head of the astrogeology branch. The radar scans did not indicate the boundary between the astonishing highlands and dark plains that Huygens traversed. Finally, a clue emerged as two singular dark sand dunes, about 30 kilometers north of the landing site, visible in both radar and optical photos. These dunes are likely composed of sugar-sized hydrocarbon grains between 100 and 300 microns in diameter. Most of Titan's dunes are enormous, up to 100 kilometers over the dark fields and separated by 10 miles. More importantly, these two dunes, visible in both radar and optical photographs, provided researchers with the data they needed to begin their study. Sodom stated that they started to develop a model of how they think Titan's surface behaves. In this hypothesis, the region surrounding Huygens' landing site is a vast plain of filthy water ice, covered by layers of organic carbon-bearing deposits that form the bright highlands and dark dunes. The bright layers are invisible to radar frequencies, allowing Cassini's radar to penetrate through to the base foul water ice layer, which is rough in some places and smooth in others. These deposits form when sunlight, UV light, and charged particles react with Titan's abundant methane at high altitudes, producing carbon and hydrogen-bearing hydrocarbon molecules such as ethane and acetylene, as well as more complex nitrogen-bearing compounds known as tholins. These products fall to the surface as aerosols, similar to how smog particles form and cover Earth's surfaces. However, on Titan, these deposits can accumulate to depths of many meters. The dunes consist of sand-sized debris that either accumulated during its descent or was reshaped by geological processes on the surface. The icy inorganic landscapes are as unique as they are striking. To the north of Huygens landing site lie the Bright Highlands, which feature channels that split 4 or more times as they flow into the hills. Stereoscopic images from Huygens descent and the DISR camera have now been analyzed, revealing that some of the ridges between the channels reach heights of 150 to 200 meters and have slopes of 30 degrees. This is very rugged terrain, explains Sodom. The layout suggests that these are drainage trenches with liquid methane flowing as rain. Nearby are thick gullies with few branches, most likely formed by spring drainage, a process in which methane seeps through the subsurface before emerging as a spring near the base of a slope. The spring erodes the slope, causing it to collapse and form a cliff face. The third section is a flat, dark plain, primarily water ice mixed with organic grit covering Titan's surface. Waterway channels, ravines, and floodplains rival the assortment seen on Earth. The dim plains reveal signs showing that the area occasionally gets flash floods, although not from the highland waste channels. Rather, vast amounts of liquid methane seem to flow east-west. Planetary researchers may now begin to reproduce the chain of events that resulted in the development of this extraordinary landscape. Huygens and Cassini have moved forward in our understanding of Titan. Soderblom said Huygens was the primary probe to land on a moon other than Earth's moon. NASA and other space organizations initially showed little interest in Saturn and Jupiter's moons. Global interest only grew after it was discovered that Titan mimics Earth in such a strange way. Since then, probes and telescopes have found countless additional moons orbiting the gas giants, each with its own particular surface conditions, volcanism, and water traces. Unlike the gas giants, which are hardly composed of solid parts, these moons are rocky, world-like Earth. When Huygens landed on Titan, it found a ruddy, harsh environment of rocks and cliffs, as well as signs of beaches. Hubble and Cassini measurements confirm that Titan has an ocean. Titan's surface is dark brown and ruddy due to organic material deposits. The region where the probe landed is dirty with water and hydrocarbons and has a consistency equivalent to damp sand or earth. After analyzing Huygens and Cassini data, it became apparent that Titan's lakes contain liquid methane, perhaps in addition to water. Methane is a colorless gas that occurs on Earth in many forms, including natural gas and biogas, and is used as an energy source in nature. Marshes and forests can make more methane. Man-made methane is produced from rice cultivation, landfills, and cattle digestive systems. Methane, along with carbon dioxide, nitrous oxide, and chlorofluorocarbons, CFCs, is a significant greenhouse gas that has a huge effect on the human-induced greenhouse effect on Earth. Does all that here eventually go against life on Titan? The failure was at first widespread on Earth. Many researchers believe that there might be methane-based life. However, more voices quickly emerged to propose that this was possible. With our limited understanding of the universe and its intriguing happenings, how can we be sure that there are no species somewhere whose organisms survive on methane rather than water and can breathe something like nitrogen instead of oxygen? Opponents argue that Saturn's moon Titan lies beyond Earth's habitable zone and, therefore, can't support basic living things like bacteria or algae. The planet and its moon receive far less sunlight than we do on Earth, Venus, and Mars. However, this condition, along with Titan's extremely low average temperature of -290 degrees Fahrenheit, doesn't necessarily rule out the possibility of life. Fish and mollusks are examples of complex living forms that exist on Earth far from sunlight and heat. Complex creatures like mollusks and fish exist in the Mariana Trench, 6 miles below the water surface, where they have never seen sunlight. Microorganisms have been found near the poles, and a variety of mushrooms, lichens, and primitive organisms survive in cold, lonely caves. So we must be cautious when claiming that life can only be sustained by light, heat, and oxygen. But what about Titan? Wouldn't it need its own magnetic field? Could this be the reason Saturn's moon might not have any life at all? Not necessarily, say some hopeful scientists. Titan's atmosphere is indeed exposed to solar winds, particularly in its outer layers. However, increasing UV and cosmic radiation levels might not prohibit the formation of life. Again, there are several examples on Earth where living organisms and algae survive well with extreme UV levels, so living under harsh conditions is undoubtedly possible. Thus, the scientists continued to search for signs of life on Titan. And they found it. After the Huygens mission, it became clear that the 32 lakes seen on Titan's surface so far are most likely filled with liquid methane rather than water. Methane becomes liquid on the Moon's surface due to the approximately 50% greater pressure. Space telescopes and the Cassini mission were able to reveal frozen seas, which turned out to be a surprising discovery. This is because subsequent measurements revealed that the sea is made of water rather than liquid methane. Scientists even expect that there is liquid water beneath a thick layer of ice with temperatures above 32 degrees Fahrenheit. If this discovery proves true, it is almost possible that this body of water harbors some form of life or a precursor, such as microorganisms or single-celled organisms. Another probe is already being prepared to test the water on Titan. A drill would need to penetrate the thick layer of ice to lower a probe into Titan's oceans. Plans to develop such drills are already underway. German engineers are developing high-performance drills in the Arctic, among other locations, to drill into the ice layers of Titan and Jupiter's icy moon Enceladus for upcoming space missions. Titanian life is possible, according to laboratory simulations. In 2010, researchers from the University of Arizona demonstrated in the laboratory that life on Titan is indeed possible. They precisely simulated the conditions in the Moon's gas shell using a combination of nitrogen, methane, and carbon monoxide that matches the composition of Titan's atmosphere. The scientists were able to produce amino acids, even when exposed to elevated levels of radiation. Those who want to witness actual extraterrestrial life or life like humans on another planet or moon will be disappointed if they only find bacteria or fungi. However, the tiniest living organisms would only be the beginning, and we humans would have to accept that we wouldn't be completely alone in the universe. As scientists learn more about Titan's structure and environment, the question remains, could Titan support life forms unlike anything we've ever seen before?